This is Laplace equation, and this is Poisson equation. So Laplace and Poisson equations appear in many branches of physics. For example, they can stand for the stationary solution of the heat equation. In the context of this course, one important application is that the Poisson equation here stands for the potential of electric fields. And this has been recently used in some softwares that are used when people try to do non-invasive brain stimulations. So they have these very interesting numerical simulations where they have domains that represent real brains, and so they simulate the fact of putting some electrodes and putting current in some part of the brains. And it's non-invasive, so it's just on the top of the skull. But the equation that is used for that is typically a Poisson equation. All right. So yeah. So next, the aim of the session is in fact to do some math after this introduction. So those are classical theorems, and so we will review them, and next time we will discuss the proofs of those results. So the first theorem is the mean value. It says that so when a function satisfies Laplacian mu equals 0, this is called also harmonic functions. Then if you choose here a ball which is strictly included in omega, then you can express u at the center of the ball as an integral over the border of the ball. And also, with a simple integration of that, you can have, so this is not the border, this is the volume of the ball, right? So I will correct that. So the second one gives, in fact, a relationship between u at the center of the ball and an integral all across the ball, not the border, right? The partial here stands for the border, but this is a typo. And you have analog results when you replace harmonic functions by superharmonic functions or subharmonic functions. All right, and this actually, the theorem 1, is the main tool that is used to prove this strong maximum principle, which says that if a function satisfies Laplacian of u is non-negative, and if there's a point in omega such that u is supremum, then u must be constant. And analog results hold if you replace here more than by less than, and the sub here by the inf. Okay, from there, when the domain is bounded, you have that, so there's a typo here also. You have that if u is a superharmonic function and omega is bounded, then um, the supremum is attained in the border.